when dealing with infinite limits, or just limits in general, it's important to note that sometimes you're going to end up with these things called vertical asymptotes. And we'd already discussed that sometimes as a function, or as an x value approaches some point, the function value becomes unbounded. It just starts going up or down to infinity. And what you'll find is, or rather how we describe that is, as those curves happen like this or down like that, we call those vertical asymptotes. An asymptote usually just means end behavior. And so what we think about is this thing is just following, it's tracking, and its end behavior is it's slowly aligning itself with this dashed line. Ever so slowly. It never touches it, but it becomes very, very, very intimate with it. And so the idea is, if, the more formal way to state this is, if f of x approaches positive or negative infinity, as x approaches c from the right or from the left, it doesn't matter, then this line, x equals c, is considered to be a vertical asymptote. Now, you could have a case where it has an asymptote on one side and doesn't on the other, but generally speaking, you're not going to have that situation. That would usually be some sort of piecewise defined function. It can happen, but it's not super common. Now, one of the big results that helps us find this is here, right? Because the problem with asymptotes is, well, how do I determine what they are? Now, sure, I can plug it into a calculator, but beyond that, how do I look at a function and go, it's going to have an asymptote here? Well, one quick way to do that, and it's not the only way, but this is a quick way to check, is if I have two continuous functions, but at some point, one of those functions is not 0 and the other one is. Again, they have to both be continuous functions. Then if I take this one, the one that's not 0, and divide it by the one that is 0, and take that function, then that asymptote will exist at that point where the bottom one is 0. Now, I kind of said that backwards because in practice, you're usually going the other way around. What you're doing is you're taking a function like this. You're saying, okay, I have some function on top and some function on bottom. Can I find a point where the bottom function is 0, but the top function isn't? So in this particular case, if I plug in -2 to the function, well, it's not defined at -2 because this bottom function would be 0 and this top function wouldn't be. So therefore, we say that function has a vertical asymptote. But be careful. Be careful that you don't just check the bottom function only. For instance, this one, in this particular function, the bottom one is equal to 0 at 3 and -3. But the issue is at the top function, if you plug in 3 to the top function, it's also 0. So what you're going to have here, with a little bit of work, is you're going to have a removable discontinuity. And since you have a removable discontinuity, you're not going to have that asymptotic behavior.